Welcome back, everyone. Have you ever actually stopped to wonder how a computer, really remembers information? At its core, a computer is literally just a massive collection of microscopic logic gates processing electrical signals. So, how in the world does a fleeting pulse of electricity get trapped, stored, and then recalled as an actual piece of data? Well, today in this explainer, we're going on a journey through the evolution of digital memory, unpacking the absolute unsung heroes of your devices, sequential circuits. Let's get right into it. Here is our roadmap for today's evolutionary journey, taking us from a basic feedback loop all the way to complex timekeeping. 1. The power of memory. 2. The circuit heartbeat. 3. Flipflops, the memory builders. 4. Fixing glitches, master-slave. 5. Shift registers, moving data. And finally, 6. Counters, keeping the beat.
Section 1. The power of memory. Moving beyond the present. Okay, let's dive into this with our very first high-level concept, which is giving a logic circuit the actual ability to remember.
To really grasp what makes our modern devices so incredibly powerful, we have to contrast two fundamentally different types of circuits. You can think of a combinational circuit as having total amnesia. Seriously, it's a logic circuit that only cares about what is happening right this exact second. Its output depends entirely on its present inputs. But a sequential circuit keeps a diary. Its output depends not just on what you're telling it right now, but also on the history of its past operations. And it's this dynamic behavior that lets systems execute incredibly complex tasks in real time.
So how exactly does it keep that diary? Well, a sequential circuit is essentially just a combinational circuit paired up with a memory element. But the real magic here, the true superpower, is the feedback path. This path literally grabs information from the output end, cycles it all the way back to the memory element, and then feeds it right back into the input start line. The system is continuously feeding its own history back into itself to figure out what it needs to do next. It's like a giant continuous loop.
Moving on to Section 2, the circuit heartbeat. Introducing the clock signal. Because, as you can probably imagine, this continuous loop creates a brand new challenge when it comes to the concept of time. If you have millions of these loops constantly feeding data back into themselves at blistering speeds, how do you avoid absolute data chaos? If signals are arriving at all different speeds, who controls the timing? That's the big question, and it was a massive hurdle in early digital logic design. Engineers solved this impending chaos by categorizing sequential circuits into two distinct types, asynchronous and synchronous. Asynchronous circuits just react to input pulses whenever they happen to arrive. They are incredibly fast, for sure, because they never sit around waiting, but they are notoriously tricky to design and can easily produce uncertain outputs. Synchronous circuits, though, they solve the chaos completely. They use a common clock signal to synchronize all the memory elements at once. Think of this clock signal as the heartbeat of the system, or like the conductor of a giant orchestra. While it might make the overall operation just a tiny bit slower, because the circuit literally has to wait for the next clock pulse to act, it absolutely guarantees a reliable, predictable operation every single time. All right, Section 3, Flipflops, the memory builders, the atomic unit of memory. Now that we've got our conductor keeping perfect time, let's zoom way down into the microscopic level to look at the actual hardware storing this past history. Number 1. It all starts right here. All the unbelievably complex data storage on Earth, every high-res photo, every streaming video, every single document begins with this single number. It's the one bit of binary data, a 0 or a 1, that a single tiny component can hold.
And that tiny component is called a flip-flop. A flip-flop is a sequential digital electronic circuit that has two stable states, and it's used to store exactly one bit of binary data. It is literally the atomic, fundamental building block of memory. This is the exact mechanism that creates the memory that retains your data even when a digital system's power is completely shut off. Out in the wild world of logic design, there are four main species of flip-flops that engineers use to build these complex systems. We've got the SR, or set-reset flip-flop, the JK flip-flop, the D, which stands for data flip-flop, and the T, or toggle flip-flop. They each have their own totally unique behavior based on the input they receive and that all-important clock signal.
Let's look at the simplest one first, the SR flip-flop. It has a set input and a reset input. You activate set, the output goes high. You activate reset, the output goes low. Super simple, right? Well, actually it led to a pretty massive engineering crisis early on. The SR bug. If both the set and reset inputs are triggered to high at the exact same time, the circuit basically throws its hands up in confusion. The output becomes an invalid state. It's a fatal bug that can just crash the logic of an entire system.
Now, what's really interesting about this slide is how engineers brilliantly solved that exact bug. They invented the JK flip-flop. It operates very much like the SR, but with a super clever fix for that invalid state. When both the J and K inputs receive a high signal simultaneously, the circuit doesn't crash. No way. Instead, it elegantly toggles its output state. It just flips from high to low or low to high. Problem solved.
Which brings us to Section 4, fixing glitches, master-slave, solving the race-around condition. Because let's be honest, evolution is messy, and fixing one problem usually creates another. The JK flip-flop sometimes worked a little too fast for its own good, causing this erratic glitch known as the race-around condition. So we needed another evolutionary fix.
The fix was the master-slave JK flip-flop. Engineers cleverly cascaded two JK flip-flops together, and here's how it works in 3 steps to brilliantly avoid that nasty race-around glitch. Step 1. The first flip-flop acts as the master and responds only to the positive level of the clock pulse. Step 2. An inverter, basically a NOT gate, completely flips that clock signal, which leads to Step 3. The second flip-flop, the slave, is now forced to act only on the negative level of the clock pulse. By making sure they never ever act at the exact same time, data is passed securely from master to slave without any of that erratic toggling. Pretty genius, right?
Moving right along to Section 5, shift registers, moving data, teaming up flip-flops. Let's zoom back out and see what happens when we start grouping these solitary flip-flops into teams. Storing one bit is great, but modern computing needs to move a ton of data around. And this brilliantly illustrates exactly how we do that. When you group flip-flops, you get a shift register, which dictates exactly how data flows in and out. We have SISO, serial in, serial out, where data moves in single file, which is great for creating time delays. Then there's SIPO, serial in, parallel out. It takes data in a single line and outputs it across multiple lines all at once, perfect for demultiplexing. Conversely, PISO takes parallel data in and shoots it out serially. And finally, PIPO, parallel in, parallel out, where the whole shebang enters and exits simultaneously. That one is widely used for temporary data storage.
Finally, Section 6, counters, keeping the beat, counting events in digital systems. We've reached our final high-level assembly today. We've stored data, we've moved it, and now we need to count it. But remember our thematic callback here. Counters are really still just cleverly arranged teens of flip-flops synchronized by a clock.
Counters tally up the events or pulses in a digital system. You've got up counters that count progressively forward and down counters that count progressively backward. But the real elegance is in the up/down counter. By adding a simple combinational circuit between the flip-flops, engineers created a mode control input known simply as M. It is brilliantly simple. If M equals 1, the circuit counts up. If you switch M to 0, it instantly reverses direction and counts down. So, what does this all mean for us? Why does it matter? Because this logic is literally the heartbeat of the modern world. Without counters, we wouldn't even have digital clocks. We couldn't measure time accurately in scientific instruments. We absolutely wouldn't have analog to digital converters, which means processing audio or video in the digital realm would be impossible. Every single time an event is tallied in a machine, there's a sequential circuit of flip-flops in there doing all the heavy lifting.
Which brings us to a pretty mind-boggling realization. From digital clocks to massive computer memory, flip-flops really are the fundamental building blocks of the digital age. We started today with just a single feedback loop, one tiny flip-flop storing a single 1 or 0. And from that atomic unit, engineers built shift registers and master-slave components to manage time and kill glitches, stacking them higher and higher to build the incredibly complex world we live in today. So I leave you with this provocative thought. Knowing what you know now about how these systems remember and count, how many millions of these microscopic sequential circuits are silently clicking away in the device you're watching this explainer on right now? Thanks for watching, and keep staying curious.